Hello, my name is Paul Hager. I'm one of the authors on the paper A Tale of Two Classes, Adapting Supervised Contrastive Learning to Binary Imbalanced Datasets. So, what is supervised contrastive learning anyway? Why do we care? Well, supervised contrastive learning is a form of supervised learning that uses also the contrastive learning loss function to create a more well-structured latent space. And so we want to learn representations where similar items are close and dissimilar items are far. And it's an extension of the unsupervised contrastive learning, as we just said, where we use the class labels during contrastive learning to further guide the learning process, gathering a single class in a specific portion of the latent space to aid linear separability. So the key principle is that we are pulling embeddings of samples from the same class together. So these are all now positives. The positives in contrastive learning is usually just one image augmented twice. Here the positives has been expanded to include all images of the same class. And we are pushing embeddings of samples from different classes negatives apart, so that part stays the same. And so it's been shown that subcon is really, really strong on balanced data, but starts to fall apart a little bit with imbalance. And so there has been a great body of work on how to adapt this to long-tailed super distributions, but binary imbalanced distributions so far have not been properly explored. And this is where we saw a real issue, because this is common in very many real-world tasks. For example, we work a lot with medical data. And here, the representation space collapses completely. The loss stops training, the embeddings of both classes cluster into a single point, you lose all discriminative power and pretty much all downstream performance. So we set out to understand this, and for this we initially started using standard metrics, the sample alignment distance or the class alignment distance, to look at inter-sample similarity or within class similarity. But we were seeing good values there even when the classes are very poorly separated. So this doesn't really capture inter-class separability. So if we take a look, for example, here, we have the linear probing accuracy on one of the data sets that we looked at in the paper. And when you go down to 1 to 99% class imbalance, or even only just 5 to 95%, the linear probing accuracy plummets to 55, 56%, whereas typically if it's balanced 50-50, you get 93.7%. And the sample alignment distance, for example, in the bottom left, the mean is pretty much the same everywhere. And the Gaussian potential uniformity also is quite high everywhere. So what we then set out to do is kind of find new metrics that allow us to better understand what is happening in the latent space here. So we came up with the sample alignment accuracy. So instead of looking at the distance anymore of samples, we want to know, is a sample's positive view closer than any other negative view? So really measuring the accuracy. Okay, is there cosine similarity highest between positive pairs compared to all other negatives in the batch? And the other thing that we want to know is class alignment consistency. So what fraction of a sample's neighborhood belong to the same class? And what this really lets us do is understand much more about how our latent space is structured in respect to how separable our classes, because the goal of supervised contrastive learning is explicitly to have use class labels to better learn a separation between the classes for downstream classification tasks typically. And this allows us to much more directly measure that. And now we find, for example, with our new SAA and CAC values, that they find good representation spaces, and they can also diagnose this collapse, which the other metrics could not. So this then led us into our fixes. How do we, now that we know what the problem is, we can see this collapse, how do we fix this now so that we can train with heavily imbalanced binary datasets that we often encounter in real life? So our first fix is very simple. but highly effective. And here what we say is, okay, we know which samples are part of the minority and which are part of the majority. And in this case, the minority class, we're going to do subcon, so supervised contrastive learning, very typical. And for the majority class, we're going to do typical unsupervised contrastive learning, which maintains uniformity and helps avoid the collapse dominated by the majority. But the minority class still has a strong subcon signal, which is going to encourage strong alignment and heavy clustering in the latent space. Our second fix is supervised prototypes, pulling on the literature for prototypes in contrastive learning. What we do is we define two class poles on the hypersphere that are on opposite ends of the hypersphere. We initialize these fixed prototypes, and then if a sample is far from its class prototype, for example, its cosine similarity is less than 0.5 to that prototype, we pull it towards the prototype, which is improving alignment. And otherwise, if the sample is already close, we apply the classical NTXN unsupervised contrastive learning laws to help maintain uniformity while maintaining its position on the unit hypersphere. And so we see that our fixes boost performance significantly. For example, we were looking at both artificially imbalanced datasets using the INAT21 dataset. A portion of that you can see here is the plants dataset. This allows us to artificially imbalance our dataset from 50-50 down to 95.5 down to 99.1. And we also used some real-world datasets containing medical images. For example, here the UK Biobank dataset, where we were predicting the chance of an infarction, which has about a 4% positive rate. And so we see, okay, subcon collapses to 54.4% linear probing accuracy, whereas subminority and subprototypes, even at 1% imbalance, restore this, gaining 31 to 29% in linear probing accuracy. Whereas on the medical image dataset, this also works in real life. Subcon, very, very poor performance at 61.9%, whereas subminority and subprototypes improve upon this by about 16 points at UC. So, as I said previously, these were the three natural image datasets where we did the imbalancing manually. We see here that our sub-minority outperforms also all long-tail data sets that you can see there in the middle on the 5% and the 1% imbalance. And our sub-prototypes is also quite strong, typically outperforming most of the long-tail methods on even 50%. On medical image data, we see similar trends. Here we see that our subprototypes is actually typically a bit stronger than our subminority. And we see that we outperform both subcon and the baseline methods on 4 medical data sets. So what's also quite interesting is that our new class alignment consistency, which to remind you is about how consistent is a neighborhood of a representation with its class. So are the neighbors in the representation space, do they belong to the same class or do they belong to a different class? Measuring this is actually a really strong indicator of downstream accuracy and downstream performance. So this is a really interesting metric to use before doing some kind of linear probing or doing some kind of supervised fine-tuning. This already will give you a really good idea of how well your representation space is formed for the classes that you're interested in. And so you can see here with RCAC, we have an overall R-squared value of about 0.69, whereas other than that, in the canonical metrics in the top row, the highest overall R-squared value was 0.045. And so this is definitely a really good metric to use if you're interested in understanding how well is your latent space formed for the classes that you're interested in. So to pull it all together, standard subcon fails on binary imbalanced data due to representation collapse. The canonical metrics of alignment, sample alignment, and class alignment distance do not reliably detect this collapse. That's why we introduce sample alignment accuracy and class alignment consistency for better diagnosis, and especially useful is our CAC for also predicting downstream utility. And we give two fixes, supervised minority and supervised prototypes, that restore the class separation and significantly improve performance up to 35% over subcon. And we show that these are effective strategies for applying subcon to real-world imbalanced binary datasets.